Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on August 1st, 2025, about a week ago. This paper provides a concise review of the essential math behind geometric deep learning, a framework that helps AI models handle complex, irregular data like graphs and social networks, which traditional methods struggle with. The paper is titled Mathematical Foundations of Geometric Deep Learning, and it really clarifies how these complex mathematical ideas connect to the models we use every day. It systematically lays out the key concepts from algebra, calculus, and geometry that are crucial for building these more advanced and generalizable AI systems. And as I mentioned, it's getting some attention on X. We can see a post here from the user Chaumian, who simply shared the title and a link to the work. It's already gotten over 80 likes, so it's definitely catching some eyes. It's clear that a good refresher on these fundamental mathematical concepts is something the community appreciates. So to really understand the contribution here, let's start with the first mathematical pillar they discuss, which is algebraic structures. And this first figure really sets the stage perfectly. It shows this zoo of different deep learning architectures, like convolutional neural networks, transformers, and graph neural networks, each represented as a different animal. The central idea here, and the whole point of geometric deep learning, is to provide a single, unified mathematical framework that explains how all these different models work. It's inspired by an old idea from mathematics called the Erlangen program, which unified geometries by studying their symmetries. This approach does the same for AI. So to build that unified framework, we start with the absolute basics, sets and maps, which are just rules for connecting items from one group to another. This diagram shows three key types. First, on the left, an injective map is one-to-one, where each starting point connects to a different endpoint. Then, a surjective map is onto, meaning every single destination point is covered. And finally, a bijective map is a perfect pairing. It's both one-to-one and onto, with a unique connection for every single element. Alright, building on that, the paper introduces the concept of a group, which is the mathematical way to talk about symmetry. This figure gives a great physical example using a square. You can rotate it by 90, 180, or 270 degrees, and it still looks like a square. This set of rotations forms a group because combining any two of them, say a 90-degree and another 90-degree turn, just gives you another rotation that's already in the set, a 180-degree turn. This is the essence of symmetry. And this idea of a group acting on an object extends directly to our data. This figure shows a perfect example of what's called a group action. So on the right, we have our original data, the Mona Lisa. The letter G here represents a transformation from our group, let's say a 90-degree rotation. When this group element G acts on the image, it produces the rotated version we see on the left. This is how we apply these abstract symmetry rules to the actual data our models see. Now, this leads to a really fundamental question. What kind of space does our data actually live in? Traditional deep learning often assumes a flat, grid-like space, but many real-world datasets are more complex. They exist on curved surfaces, or what mathematicians call manifolds. This figure shows exactly that. The curved surface is the manifold. And if you want to find the shortest path between 2 points on that surface, it's not a straight line. It's this curved path called a geodesic. This is key for understanding relationships within complex data. This brings us to a core idea in machine learning called the manifold hypothesis, which this figure illustrates beautifully. Imagine the entire space of possible images of a certain size. That's this large enclosing box representing a very high-dimensional space. Most points you could pick from this space are just random noise, like the static we see here. But a small, curved surface within it, the manifold, contains all the real images, like a recognizable face. The hypothesis is that complex data actually lives on these simpler, lower-dimensional manifolds, which is why AI models can learn from them efficiently. So, the manifold hypothesis really helps explain the power of this whole approach. By embracing the mathematics of symmetry and geometry, geometric deep learning provides a unified framework for building more robust and efficient AI models that can handle complex, real-world data. That's it for this episode of